Assalamu alaikum. My name is Zohran Bashir and my group members are Khwaja Abdul Rafe, Muhammad Salman and Sayyid Muhammad Anis. Today we will be presenting CFD structural, transient and dynamic analysis of a helical vertical axis wind turbine. So why helical vertical axis wind turbine? Because it operates at low to moderate winds. Uh, it has low torque and performs well in turbulence. My part is of about the CFT model and its boundary condition are given in the tables. We used steady runs with multiple reference frame used for time average rotor force. The inlet velocity was about 3 meter per second and we operated at 415 revolution per minute. So these are the material properties used in structural analysis. We use structural steel, PVC and wood. And for CFD computational domain setup, we used upstream of 5 times the rotor height, downstream 15 times the rotor height to proper flow, walls of 5 times the rotor diameter, inlet, outlet, and wall set to mimic real wind, keeps the turbine loads accurate, avoids domain interference. So these are our CFT results. As you can see, all residuals reduce and stabilizes, indicating numerical convergence and a steady state solution. And so these are our flow control and turbulence parameters, which include static pressure, velocity magnitude, and turbulent kinetic energy. The peak static pressure was about 53.1 Pascal, appears at rotor edges, showing current flow pattern. And these are our CFD streamline analysis aerodynamic results. Streamlines show airflow behavior around the turbine. 500 were used for clear flow visualization. Zoomed view highlights wake formation behind the rotor. Weak region indicates energy loss and turbulence effect. So our torque comes out to be 0.55 Newton meter and drag of about 1.172 Newton, and the power was about 25 watts.
Static structural analysis. For the static structural analysis, we fix the base of the turbine to represent the real mounting conditions, and then we applied the load magnitude of 1.170 Newton, which we get from the results of CFD. This helps us study how much stress and deformation will develop in the turbine structure. The This slide shows the FEM model setup including the mesh and load application. The turbine was divided into small elements of about 100 millimeter. Yes, it was 100 millimeter. Let me check. Okay, so the meshing size was 100 millimeter. And it was chosen because of accurate. For the results we get will be more accurate. The force was applied on all the three blades while the center rod was kept fixed. This setup help us understand how the wind load is distributed throughout the whole structure. The results show that the maximum stress is 19.43 megapascal, which is below the material strength limit. The factor of safety thereby is 2.57, which means our design is safe under working conditions. The deformation is also very small, so the turbine keep its shape and remain stable during operation.
Now moving towards the transient simulation results, this part focuses on the capturing the real-time behavior of the turbine, which is more realistic compared to steady state analysis. As shown in the slide 12, we can see the residuals and force plots for transients case. The residuals show a smooth decay, which indicates the solution is numerically stable, and drag due to flow adjustment and wake development, but after a short period, both values stabilize. The important point here is that the torque reaches around 0.85 Newton meter, which is significantly higher than the steady state value. So this shows the transient analysis captures the actual rotating behavior of the turbine more accurately. Now moving on, this slide shows detailed flow field characteristics, including velocity, vorticity, and turbulent kinetic energy. The velocity contours clearly indicate the acceleration of airflow near the blades, while the vorticity plot and highlights strong rotational flow and vortex formation behind the turbine. This wake region represents energy extraction from the wind. The turbulent kinetic energy plot shows how turbulence develops and dissipates downstream. Using the obtained torque value and rotor speed of 415 rpm, which is equivalent to 43.4 radians per second, the calculated power output comes out to be approximately 37 watts.
Sir, my name is Khwaja Rafe. So now I will be discussing about the explicit dynamic analysis which we did by ANSYS Autoden to study the turbine structure behavior under realistic dynamic conditions. So the Lagrangian model was basically used with approximately 182,000 elements and around 49,000 nodes. And this ensured high accuracy in stress distribution. An initial angular velocity of 43.4 radians per second, equivalent to 415 rpm, was applied to simulate actual turbine rotation. Additionally, an aerodynamic force of 1.172 newtons obtained from CFD analysis was applied, and a very small time step of 1 into 10 to the power minus 4 seconds was used to capture transient structural response accurately. In this slide, the structural mesh and loading conditions are shown. A fine mesh was used across the turbine to ensure precise stress and deformation results. The aerodynamic force was applied as a concentrated load on the rotor blades, while rotational motion was introduced using the initial angular velocity. The central shaft was fixed to represent realistic mounting conditions. Here you can see the results of explicit dynamic analysis, which show us the equivalent von Mises stress and total deformation of turbine. The maximum stress observed was 38 megapascal, and the factor of safety is calculated to be approximately 1.31. This indicates that the structure is safe under dynamic loading, although it is closer to material limit compared to static analysis. This slide presents fabrication details of wind turbine. The base was constructed using Lasani wood, which was CNC cut for precision. The structure was assembled using screws, and support angles of 30 degrees were used to ensure stability. A belt mechanism was also incorporated for power transmission. Finally, this slide shows the complete mechanical structure of the turbine. Design ensures proper balance, smooth rotation, and structural stability during operation. In conclusion, the explicit dynamic analysis confirms that the turbine can safely operate under real working conditions, and fabricated design is both practical and efficient. Thank you.